Okay, so for the majority of this course, we're going to be using induction to prove properties of programs. So here's a program written in Haskell. What does it do? If the function is given an input of 0, it returns 1. And if the function is given or some other input n, it will compute 2 times mul of n take 1. So it's a recursive function. And we would like to prove for all n greater than or equal to 0, mul of n is equal to 2 to the power of n. Okay? So in this case here, my base case is 0, and you can see that by the definition of the function. So how am I going to prove this? We're going to prove it via induction. So we need to prove for all n greater than 0, mul of n is equal to 2 to the n. So how do we do that? Do it just like we did before. We have to prove the base case is true. We have to prove the step case is true. So the base case, I need to prove that this statement is true for n equals 0. So I need to prove mul of 0 is equal to 2 to the 0. So I'm going to start with the left-hand side. I should give these rules some names. I'll call this rule M1. I'll call this rule M2. So the left-hand side is mul of 0, which is equal to 1 by M1, by the definition of mul, and 1 is equal to 2 to the 0 by math. It's usually good, it's good practice to, every single line is to be notated by a rule, which is either the definition of the function or a function, or just by math or by arithmetic, okay? So I've shown, what's 2 to the 0? 2 to the 0 is the right-hand side. So I've shown the left-hand side and the right-hand side of the formula agree for n equals 0. So the base case is proven. Now we're going to prove the step case. So how to prove the step case? We assume the formula to be true for some value of k. So I'm going to assume that mul of k is equal to 2 to the k. Okay? I'm going to give this name a rule, call it IH. Again, that's short for inductive hypothesis. The inductive hypothesis is the thing you assume when you try and do a proof by induction. Okay? So I'm assuming this to be true. And I want to prove that the formula is still true for n equals k plus 1. So I want to prove that mul of k plus 1 is equal to 2 to the k plus 1. Okay? Start with the left-hand side. Mul of k plus 1. What's this going to be equal to? Well, have a look at the definition of mul. Mul of n, for any n, is equal to 2 times mul of n take 1. So for n equals k plus 1, we're going to get 2 times mul of k plus 1 take 1 by m2, by the definition of mul. Now k plus 1 minus 1, they cancel out. So that's equal to k, 2 times mul of k by math. Okay? This part here looks like my inductive hypothesis, so I can replace it. So this is going to be equal to 2 times 2 to the k by the inductive hypothesis, which is equal to 2 to the k plus 1, which is equal to the right-hand side here. Cool. It's proven for the base case, proven the step case. So therefore, for all n greater than or equal to 0, mul of n is equal to 2 to the n. And the statement is proven. As an exercise, I'd like you to prove a property about this function here. So I've defined a function plus of 0 is 0, plus of n is equal to n plus of n minus 1. So here's the definition of it. I'd like you to prove for all n greater than or equal to 0, plus of n is equal to n times n plus 1 and 2. So this example was deliberately chosen to be very similar to the example I did earlier. So have a go at that.